Hello Chemist Corner, and welcome to Electrochemistry. Today we will look at redox reactions. The first question we need to ask is, what is meant by oxidation and what is meant by reduction? Originally, oxidation meant a reaction with oxygen to form some sort of oxides. A good example of this would be the combustion of methane bubbles. And certainly, in this reaction, the carbon in methane is getting oxidized. Well, the carbon does get oxidized into carbon dioxide. This is only half of the story of this reaction. The other half is the oxygen is being reduced from molecular oxygen to the oxide. Reduction then originally meant turning ores into pure metals, resulting in elemental metals. This became too restrictive, and so the new definitions of oxidation and reduction are: oxidation involves the loss of electrons, and the charge on the species becomes more positive. Reduction is now the gaining of electrons, and the charge on the species becomes more negative. For example, zinc 0, that is neutral metallic zinc, can be oxidized to zinc 2+ when it loses 2 electrons to hydrogen. Hydrogen, that is hydrogen ions, are then reduced to hydrogen gas by the gaining of the 2 electrons that zinc lost. This is the reaction that occurs when hydrochloric acid reacts with zinc in the following example. In this example, I'm using 12 molar hydrochloric acid with metallic zinc to produce both zinc ions and hydrogen gas. The proof that there's hydrogen gas is when I go to light it with a candle and we get that characteristic pop and a little flame. Hydrogen is now being burned by molecular oxygen to produce water vapor. This is an example of a redox reaction. The loss of electrons, oxidation. The gaining of electrons, reduction. We like to use the mnemonic, Leo the lion says grr. Leo, loss of electrons, oxidation. Grr, gain electrons equals reduction. In this example, the chloride ion becomes molecular chlorine and gives up 2 electrons. Loss of electrons, Leo. Iodine gains those same 2 electrons to form the iodide ion, Gur, gains electrons reduction. For oxidation to occur, reduction must also occur at the same time. Since both reduction and oxidation occur at the same time, the resulting reaction is called a redox reaction. The iodine becoming iodide is reduction. The chloride becoming chlorine and giving up 2 electrons, that's Leo, that's oxidation. Together, iodine reacting with chloride ions to make chlorine and iodide is a redox reaction. Another possibility is bromine can gain 2 electrons to become 2 bromide ions, and that's the reduction half cell. Lead loses 2 electrons to become a lead 2+, that's the oxidation half cell. Put together, they form a redox electrochemical cell. Often we'd write this as a synthesis reaction, bromine and lead forming lead 2 bromide. Another example, copper 2+ can gain 2 electrons to become molecular copper in the reduction half cell, while aluminum loses 3 electrons to become aluminum ions in the oxidation half cell. In this example, I'm putting a little bit of hydrochloric acid as a catalyst, some copper 2 chloride crystals go into solution to make a pretty blue color, characteristic of the copper 2+ ion. And then I put in simply metallic aluminum in the form of aluminum foil. This spontaneous redox reaction will produce aluminum ions and copper metal. However, this electrochemical cell is not charge balanced. It's matter balanced, 1 copper, 1 aluminum makes 1 copper and 1 aluminum, but the copper has a 2+ charge and aluminum has a 3+ charge. So in order to make these charges balance, I must multiply the reduction half cell, the copper half cell, by 3, and multiply the oxidation half cell, the aluminum half cell, by 2. This gives me a total of 6 electrons being transferred from the aluminum to the copper ions to form copper metal and aluminum ions. As you can see, this reaction is quite vigorous, and the evidence is very clear. The copper 2+ color of the solution, the pretty blue color, goes away very rapidly, as does the silver color of the aluminum foil, replaced by a colorless solution and brownish red precipitate, which of course is the copper 0 metal. The 6 electrons gained by the copper ions are the same 6 electrons lost by the aluminum, and this reaction is now charge balanced. The result, after several minutes, the copper metal sinks to the bottom as it is more dense than the solution, replaced by the aluminum ions in solution, which are clear and colorless. Electromotive force, or EMF, is the amount of energy supplied to a charge to be moved, that is, the electron, by an electrochemical cell. We use the capital letter E to signify electromotive force. Electromotive force with a degree sign on it indicates this is at standard conditions. In the case of electrochemistry, standard means the ionic concentrations of any solution are 1 molar. We are in water, and the temperature is 25 degrees Celsius. That's what E0 means. 1 molar in water at 25 degrees. For an electrochemical cell to be spontaneous, the electromotive force for the overall cell must be a positive value. The cell's electromotive force is calculated simply by adding the electromotive force for the oxidation half cell plus the electromotive force for the reduction half cell. That is E0 oxidation plus E0 reduction equals E0 cell. If E0 cell is greater than 0, that is a positive EMF, which will correspond to a negative delta G, Gibbs free energy, and this electrochemical cell will function. It will work. In this example, silver only gains 1 electron while copper gives up 2 electrons. And we know it's the same electrons being transferred. Therefore, I need 2 silver ions for every 1 atom of copper. Let's look at how this reaction actually works. If I simply take some distilled water, add some silver nitrate crystals, I will produce some silver 1+ ions in solution. The nitrate will just be a spectator ion. If I take a solid piece of copper and place it in this container, now my electrochemical cell can function. The silver ions can remove 2 electrons from the copper atoms to produce metallic silver and copper ions. The voltage of this electrochemical cell is now positive 0.46 volts. Therefore, this reaction will work. The delta G, Gibbs free energy, will be less than 0. Let's take a look. We can see right away it's working. The copper is dissolving into copper 2+ ions, forming a light blue solution. If you look carefully at the edges of the copper metal, you can see it's growing. Yes, the silver ions are forming silver metal and growing on that copper electrode. Note that the 2 electrons gained by the silver ion are the same 2 electrons that have been lost by the copper. The E0 cell is positive, therefore this reaction is spontaneous. And here is the result. The spontaneous electrochemical cell produces silver metal, which now coats the copper electrode. The copper metal has been oxidized to copper 2+ ions and goes into solution, forming a light blue solution. You may notice that the light blue solution is darkest at the top and the bottom of the container and very little in the middle. The growth of silver on the back of the electrode is something out of modern art. If you have any questions about redox chemistry, please feel free to leave a comment in the comment section. If you enjoyed this video, subscribe to my channel, tell your friends.